like the previous talks, also my talk is on models, see? And in particular, a particular type of models. I don't know if this kind of model, mixture models, fit in what told us Giuseppe De Gaetano yesterday. Okay. So I introduced mixture of models, mixture of densities. So what are some applications? And then I will introduce the mixture reduction problem, giving some motivation. And then we'll formalize the problem. And then we will see that there are some problems in this problem, some issues. And the composite transportation dissimilarity framework can solve some of these issues. And in particular, an adaptive mixture reduction algorithm can be devised and with some properties. We'll see. Numerical tests will confirm these properties, so we give conclusions. So what are mixture of densities? They are just convex combination of densities in elementary classes. So mixture of Gaussians, exponential, Bernoulli, any kind of class you can imagine. So you have a vector of weight that sum up to 1. So they can be interpreted as probability masses. So we will write mixtures like summations. So these are equivalent ways of writing mixtures. And in the case of Gaussian mixtures, the most popular mixture used by scientific community, you have a vector of parameters that are the mean values and the covariance of the components. So these are n components, and will be the size of the mixture, right? So a mixture of large size has a large number of components. Mixture of small size has a small number of components. And here you have the vector, the set of parameters theta that is made of the set of the weights that sum up to 1, and then the set of mean and covariances. So this set of parameters univocally defines the mixture. So mixture, in particular, mixture of Gaussians are universal approximators of density. So when you have a complex system where the stochastic, the uncertainty can be modeled only in some complex way, mixtures are very useful. Some applications of Gaussian mixtures, these, in particular, they are very well known and used in clustering and pattern recognition problems in all application fields. So from image segmentation in any fields, so for object recognition, background removal of images, medical and security applications, anomaly detection, so for fraud detection, network security, speech or speaker recognition, in finance for clustering market or customers, and so on. So I just hoping to attract your attention. So interesting. For instance, for this workshop, I just collected some random examples of uses of Gaussian mixtures in biomedical applications. So I found this paper of 1972. I think this is the first one that uses Gaussian classifiers. That's the name they give to this in that paper for classifying leukocytes in the blood. Here are other biomedical applications, which you can read, but there are many fields, as you can see, from genomics and image segmentation and so on. Okay. Those of you who are interested in diabetes, I collected some papers. So you see that this tool is used also in this section, and here are some applications in engineering in general. So you have also geophysics, security, so a lot of applications. But I think most of you maybe are familiar with Gaussian mixtures. But for those who are not, I'm going to give some example of interpretation of a Gaussian mixture, Gaussian or any other density. Okay. Assume that you have a mixture of that is a combination of 6 Gaussians, each one with its own weight. How to draw a sample from this density? It is made in 2 steps. First step is to draw like a dice with different probabilities, of course. So you extract one Gaussian, and then you extract a sample from the Gaussian. So Gaussian here are represented as usual as ellipses, right? That are related with the covariance matrices. So you have these samples. Now you have samples with labels. Labels are colors. So for each sample, you know which is the Gaussian responsible for that sample. You see that here you have clusters, okay, of samples, and the clusters are not separated, so they overlap. If I remove labels, I can say, okay, maybe there are clusters, 6 clusters, but just because I remember the previous picture, right? So you can consider the reverse problem, that is finding clusters or find a mixture of Gaussians that generated these samples. For clustering, you have other methods. For instance, k-means, very well-known method, but this is a hard clustering method. So each sample belongs to only one cluster. And when clusters overlap, this is not a right choice. So, so this is the clustering you will do with k-means. The problem with k-means, a problem is that k is unknown, so it is not easy to establish what is the right k. But you can do the same with the Gaussian mixtures. There is a well-known algorithm that is the expectation maximization that maximizes the likelihood of a function. So you can reconstruct, you estimate the model, okay? You estimate the mixture that generated this data. Then you can assign labels. No, you can assign probabilities. So for each point, you have a probability. For instance, a point very close to this mean, you can say that you have a large probability that this is responsible for this generation, but points that are around this zone, you are uncertain. So maybe you have points that maybe can be generated from this Gaussian or from this other. So this is the use of Gaussian mixtures for soft clustering, so a machine learning tool. However, also in this case, you have a problem. How many clusters are in this data? When you run an expectation maximization algorithm, you must choose the number of components, like in the k-means. So you don't know if you are making overfitting, so taking too much Gaussians, or if you have the right number. So in this context, you can understand that I can try a large number of components and then try to reduce the model to see what are the true number, the actual number of clusters in a sample. So this is a one-dimensional example of a mixture made of 20 Gaussian components, and you see that with 6 Gaussians, you have a good approximation of the mixture, the previous mixer. So there is some idea that there may be some method that can that allow you to make reduction without losing information, without losing the shape. So we will consider, in general, this mixture reduction problem. That is the following one. If you have a mixture that we label A, so PA, this is a combination of NA, a large number of components, and then the problem is to find a mixture of, with a lower number of components, such that we will formalize this. The two mixtures are similar, are close enough. So we will see in what terms. Of course, from an operating point of view, you need to find the parameters of the mixture B that approximates the mixture A. Okay. So this parameter space is important in this case because actually any computer works on the parameter space unless, okay. Okay, in most algorithms, most applications, the target number is given. This is due to some motivations. I will give a motivation in the next slide. So NB is not the minimum number of Gaussians, in this case, or densities that can adequately approximate the original one, but is a fixed number depending on the application. I discovered this kind of problem with this problem, single target tracking, single but also multi-target tracking. When you have a target in the field of view of a sensor that provides measurements and false alarms, so at each time k, you measure something that is clutter or something really related with the measurements. You don't know. You can also you can only do hypothesis, data association hypothesis, and there exists for this problem multi-hypothesis filters. So it's known that the optimal estimate is the conditional probability density of the state given all observation from 0 to current time k, and there is a way to compute iteratively this multi-hypothesis filter. The problem is that this multi-hypothesis filter provides mixture of Gaussian. The number of Gaussian grows exponentially with time. This is the structure of a multi-hypothesis filter. So a summation that is actually a mixture of Gaussian. You have weights, you have the Gaussian distributions, and you have the number of hypotheses that grows exponentially with time. So mixture reduction is necessary because after a few steps, you would have an infinite number of Gaussian. So for these filters, this is a picture of what can happen at a given instant. Of course, these filters are not bidimensional, but dimension may be very high. I just can only plot 1 and 2-dimensional examples here. But you imagine that it's the conditional estimation of the state at time k. At the next time, after a new measurement, each hypothesis explodes in a number of hypotheses. So if you don't do reduction, you cannot use this kind of filter, of course. So so this is again what is the mixed reduction problem. Find a mixture of smaller size that is closer to the original mixture. There are many dissimilarity measures that formalize this. So how different is a mixture from another? The main properties is this function, this dissimilarity. We call this D measure because it can be dissimilarity, divergence, distortion. Names may be different. So D measure for short. D measures are strictly positive and are equal to 0 only when the two mixtures coincide. But most of these measures are not distances. They are not even symmetric. Here I have some examples. The most famous one is the Kullback-Leibler divergence. This is the expression. You have this is not symmetric. There are some symmetrized versions, artificially symmetrized versions. There are a lot of measures of the divergences, but the one with some meaning in terms of information theory is the Kullback-Leibler. So we will use the measure for our purposes. Although this framework is very general, so can be applied with any measure. So the theoretical formulation of reduction is this one. If you have a given size, the target size for the reduced mixture, for instance, you have an original mixture PA of 10 components, 1,000 components, and you want to reduce to 10 components, minimizing the divergence, so the dimension. This problem is very difficult to solve because it's nonlinear, non-convex, constrained. Imagine Gaussians. You have the variables that are covariances must be positive definite. The weights must be positive and sum up to 1. And But the main problem is that all the measures I showed you before have no closed form. You cannot compute this unless you don't make numerical integrals over volumes. So they are untractable. So good theory, but this cannot be done. Okay. So most approaches for mixture reduction are heuristic. Okay. In particular, a greedy heuristic. Okay. Greedy heuristic means that all these methods provide a sequence of mixtures of reduced dimension. Okay, so starting from 100, 99, 98, and each mixture should be similar to the previous one. And at each step, a greedy heuristic makes pruning, so it eliminates, remove components that are rated negligible, according to some cost, or two components are merged, are fused in one. Okay. Here you have a paper with a survey of this kind of algorithms. But generally, existing algorithms are that are not consistent with a unique measure. So the choice of which component to prune or remove, or the pair of components to merge, and how merge is performed. So if you merge two components, how do you compute the single components that best approximates the two that you are removing? So they are metrics. And what is the purpose? So there are steps that are not coherent with a unique measure because of this technical difficulty that you cannot compute in closed form the divergence between two Gaussian mixtures. And so, this is another issue. That is the number, in general, the number of components of the reduced mixture is defined. I didn't tell this before, but for instance, in the case of target tracking, you have an hardware that can deal a maximum of components. So if my hardware can deal with 20 components and not more, my reduction must be 20. 20 is too large or too small. I don't know. I can handle 20, so my reduction will be 20. So this is the common approach. Well, there is this framework of the composite transportation dissimilarity that allows to solve some problems. What is this CTD? It's a new measure. If you choose a D measure, for instance, Kuhlberg-Leibler, you can define a surrogate D measure in this way. This is the solution of an optimal transport problem. You only need to compute the divergences between pairs of components, and this in general are in closed form. For instance, for Kuhlberg-Leibler and Gaussian, you have a simple closed form that gives distances between single components. You need only this. You formulate this problem. This is a transport problem. The matrix that is unknown is the stochastic matrix with marginals, the set of weights of the origin of mixture A and the set of weights of mixture B. And so the optimal value of RW is the optimal transport map. The CTD is the cost of the optimal transport plan between two mixtures. This picture is maybe you can explain better than I can do. Here you have a mixture of 4 components. Here you have a mixture of 3 components, but can be also 4 or 5 other components, and no matter. These are the weights that sum up to 1. These are the weights sum up to 1. And this is an optimal transport problem. You must transport weights from these nodes to these nodes. The cost of transportation of a unit mass from one node to another is given by the divergence between the two components. So this is the divergence between first and first Gaussian. This is the divergence between the first and last Gaussian, and so on. This is a linear programming problem that can be easily computed. And the property is that this CTD is a measurement easily computable of the underlying dimension, and lends itself to the derivation of reduction algorithms. This is what we did in this paper, not only actually for Gaussian, but for any mixture, any class of densities. And the interesting fact is that this bound is rather strict when the two mixers are close. So when the mixers are close, actually this bound is very strict. When this mixers are far, this bound can be not so strict. So the idea is to minimize this bound and while keeping small this value. And this allows a coherent greedy reduction algorithm. So all criteria are developed between the same, according to the same D measure. Okay, and moreover, we have two criteria for stopping the reduction. So that we can perform reduction not until a fixed number of components, but until this cost remains small. So we can fix a threshold on this cost and then stop the reduction. We have two criteria for this. We will see soon. A key point of the algorithm is the computation of barycenter submixer. A D barycenter, D because the barycenter depends on the D measure chosen, right? So we consider often the Kullback-Leibler barycenter. The barycenter of a set of weighted Gaussian, not necessarily a mixture. You have a set of Gaussian with own weights. You can find a Gaussian that, in average, is the closest one to all Gaussian in the set or in the mixture. So the problem is formalizing this in this way. And the Kullback-Leibler barycenters are very easy to compute. For other dimensions, we developed some fixed point therapy computations. So this is the Kullback-Leibler again, and this is the formula for the divergence between two Gaussian in closest form, right? Remember that no closest form exists for the KLD between mixtures, but for single Gaussian we have this, and we exploit this. So what is a barycenter? These are the formula for the KLD barycenter. This is the mean value of the single Gaussian, the best. So the barycenter is the single Gaussian that best approximates, according to the Kullback-Leibler, the mixture. Not a very good approximation, as you can see, but that is one. The mean is the average of the mean values of the components. The covariance is something more complicated. It turns out that our algorithm provides barycenters of clusters of Gaussian. So here you have an approximation that is made by a two components mixer that are the barycenters of this mixer. So this is with two barycenters, you have a good approximation of this mixer. But in general, what is a greedy CTD reduction? The reduction algorithm produces a sequence of mixture of densities, maybe Gaussians, with decreasing size. So you start from the initial mixture and ends up to a mixture of a prescribed size, NB, or maybe you can find this number in an adaptive way. We will see this soon. At each step, a submixture made of two components is merged into its barycenter. So we must select which pair in a mixer are sufficiently similar to be merged. And the criteria is to minimize the reduction cost, one-step cost. So the is an incremental cost. When we perform one-step reduction, we know what is the loss, the information loss on the mixer. So this is formally what we are minimizing. The update is made in this way. The new mixer is the previous one, when we remove the two components and replace them with the barycenter. The weight remains unchanged because the barycenter has a sum of weights that is the sum of the weights of the removed component. Okay, it turns out that for Gaussian mixture and KL divergence, this algorithm is exactly an algorithm developed in 2007 by Randall, and it is indeed the most accredited reduction algorithm. But we gave a meaning to this algorithm derived in another way in this framework, right? But what about the size? As I said, in most applications, the number of the components of the reduced Gauss mixture is limited by the computational resources, or maybe the number of real clusters in data. This is another. This is the interpretation when we use this in target tracking, for instance. But maybe we can try to find the real patterns in data using this reduction. So the NB can be too small or too large. As I said, we developed the two costs, two indexes that provide criteria for stopping the sequence when the cost is too much. So this cumulative merging, the relative cumulative merging costs are CMC, developed in 2002, and then in 2003, the normalized incremental costs. Rapidly, when you can imagine the sequence, the reduction sequence until one single component. We can prove that this single component is the barycenter of the original one. So we can compute in one step these components. And we can compute the cumulative cost, the sum of the cost at each step, normalized to the worst case cost. The worst case cost is the cost of approximating a mixture with the barycenter. This is the maximal cost. So we have a relative cost, a sequence of numbers that has its maximum at 1, and then we can fix a threshold and stop the reduction when this threshold is overcome. Right? There is another index that is the normalized incremental cost. We have a bound of the cost that we have at each step, and so we have another index that says at each step how bad is the cost, okay, the reduction, how bad is the reduction of one step without computing a cumulative cost. Okay, let's see some plots. This is a mixture with 20 components, and here I report the number of components. We start from 20. This is the original mixture. We perform reduction, and we see that after when we reach 11 components, we still have a almost perfect copy of the original one. The two indexes, the RCMC and NIC, are below 0.1. This in orange is a band, a typical band where we can put a threshold. 0.1, so 10% of the worst case, or 20%, or 25%. We see that from 11 to 10, we miss this one. So we lose this information, but the cost is not enough. So this is not evaluated, it's not a great loss. From 9, 8, 8 is still a good approximation. 7, 6, we are entering the threshold zone, right? So it depends where we put the threshold. However, we have still a good approximation. Now, from 5 to 4, we miss this. We lose this other spike. Okay, this is quite more important in both the indexes. But the real loss is when we pass from 4 to 3. You see, we completely lose the two bumps. Okay, now, for one-dimensional case, we can check this as humans with our eyes. But imagine what happens with a mixture in n dimension. you cannot visualize this kind of thing, but this, yes, you can visualize this. So when you find that the costs, one or both, increase suddenly, you know that maybe you should stop the reduction. Okay. This is another example without bumps. Remember that there are some skewed terms. Again, until 9 components, you have practically no loss. 8, 7, 6. In 6, from 7 to 6, you have this loss that depends on where you place the threshold. So you see what happens. This plot is to show that in general, the red curve, the nick, has a change in slope that is more rapid than the green one. So it's in many applications, it's a very good indicator of when we should stop. So from 4 to 3, you see what happens. So this is a loss. So maybe the idea is to use, we found actually that 0.15 is the best value in many numerical tests that we did, right? So in the band, we can have this kind of thing. The incremental cost says this, that you can have these flat regions. That means that what you are losing from 4 to 3, you see, from 4 to 3 components is has the same cost of what you get from 3 to 2. This is the flat region. Okay, this is the cumulative cost increases. The incremental cost can be flat. This is a benchmark example in this paper, and we see that choosing a threshold of 15%, so 0.15, actually we have that the one criterion, the green one, would suggest 5 components, and this is the blue curve, while the red criterion suggests 6 components. 6 components overlap almost perfectly on the original Gaussian. So we trust maybe more on the nick, the red criterion, because its slope is steeper, and this, what does it mean, a steeper slope? A much more independence on the choice of the threshold. You can change the threshold. So in this example, you can choose a threshold between 0.1 and 0.2, you always get 6 components. So it's more robust because you have a slope. This is a bidimensional example. We generated artificially a Gaussian mixture where we draw randomly a number of Gaussian, 6 in this example, that are cluster centers, and then Gaussian components randomly around Gaussian. So we know that generated this example, this mixture, around clusters. So we are asking, our method will recover the exact number of clusters. Here is what we get. The nick, the red curve, is much more steep, and recover the. Okay, here you have 6 that is not represented. 6 is still tolerable. 5, no, because there is an increase in the cost. And the increase is due to the fact that actually you have 6 clusters. So this method revealed the 6 clusters. So you have this Gaussian mixtures. The cumulative method with the same threshold revealed 9 components. Then it revealed 6 components, the right number of components. Note that if you do these experiments on real data, you are not sure about how many clusters are in real data, because you don't know in general. So this is on artificial data, because we know that there are 6 clusters. And we are happy that our method revealed this. Okay, this is just to see that we apply this method in the mixed reduction in target tracking, and had very good results in terms of performance, like tracking error or track loss percentage with respect to other methods. So with the less use of resources, less components, we are able to track the target. Okay, I hope this was interesting. So just I presented the CTD framework that allows the definition of a coherent and efficient, because I didn't stress this point, but computations are very easy and straightforward. So it's a very efficient mixed reduction algorithm. And we developed 2 indexes for reduction costs. Maybe the best thing we can do is to use both to decide when to stop. So we have 2 possibilities to decide when stopping the reduction. And numerical tests, as I showed to you, I think they validate the approach. Okay, thank you.